Hi there, future scientists. I am Atom. Embark on this exciting journey with me as we explore the concepts of energy and delve into the intricacies of the work-energy relationship and law of conservation of energy. As we discussed in the previous video called The Physics of Work, work is calculated using the following formula. Work equals force times displacement times cosine theta, where work is in joules, force is in newtons, delta D or displacement is in meters, and theta is the angle between the force applied and the direction of the displacement. For example, when you climb stairs, you do work on your body. Since you're moving against gravity, in this case, the force F is your own body weight, and delta D is the vertical height of the stairs, and the angle theta will be equal to 0 degrees. So cosine 0 is equal to 1. So work done would be just equal to your body weight multiplied by the height of the stairway. So what is energy? In physics, energy is the ability to do work or cause a change in a system. In order to understand energy and the relationship between work and energy, let us explore the sport of platform or springboard diving. Endo, of mass 55 kilograms, climbs up a vertical distance of 5 meters to do her platform diving. Did she do any work? If yes, how much? Yes, Endo is doing work on her body because she is moving her body weight of 550 newtons against gravity and is undergoing a vertical displacement of 5 meters in the same direction as the applied force. So work done by Endo on her body equals force times delta D, which equals 550 newtons times 5 meters, and that is equal to 2,750 joules. Now, the question is, what happened to all the work? Ignoring all losses, the work done is stored in her body as potential energy. What is potential energy? Potential energy is the energy stored in an object due to its position or state. There are various forms of potential energy. Gravitational potential energy is associated with an object's position relative to a reference point, often the Earth's surface or the ground. Chemical potential energy is the energy stored within the chemical bonds of molecules such as food molecules. Elastic potential energy is the energy stored in objects when they are stretched or compressed. It is associated with elastic materials that can return to their original shape after being deformed. What type of potential energy does Endo have as she stands on the platform 5 meters above the ground? The kind of potential energy Endo has right now is GPE, since she is at an elevation above the ground. How do you calculate the gravitational potential energy? In the case of an object being lifted or moving against gravity, the work done is given by the force applied multiplied by the displacement of the object. W equals F times delta D. Here, F is equal to mass times acceleration due to gravity, or F equals mg, which is the weight of the object. Delta D is the vertical height. Therefore, we can rewrite the formula for work as W equals mgh. This work done against gravity is stored as gravitational potential energy in the object. Thus, GPE equals mgh, where m is the mass, g is the acceleration due to gravity, which is 10 meters per second, and h is the vertical height above a reference point. Or we can say GPE equals weight times height above a reference point, since mg equals weight. Higher the weight, higher the GPE. Higher the height, higher the GPE. Therefore, ignoring friction losses, Endo's GPE equals mgh, which equals 550 newtons times 5 meters, which equals 2750 joules. As you can see, the work done on her body is now stored as GPE. Now, when Endo dives, ignoring friction losses, all her potential energy is converted to energy of motion or kinetic energy. So what is kinetic energy? Kinetic energy is the energy an object possesses due to its motion. How do you calculate kinetic energy? The formula for kinetic energy is given by Ke equals 1/2 times mass times velocity squared, or Ke equals half mv squared. The kinetic energy is in joules, mass is in kilograms, and v is in meter per second. This formula shows that kinetic energy is directly proportional to the mass of the object and also directly proportional to the square of the object's velocity. This means that an object with a greater mass or a higher velocity will have a higher kinetic energy. Since all her potential energy is converted to kinetic energy, Endo's kinetic energy right before hitting the water equals 2750 joules. After Endo hits the water, ignoring all losses, all her kinetic energy is used to do work in the water. Which variable, mass or velocity, would have a greater effect on the kinetic energy of an object? Velocity, because v is squared. What is work energy theorem? Work energy theorem states that work done on an object changes the energy of the object. Now, let us explore the idea behind the work energy theorem using two scenarios. In scenario number 1, which is about lifting a crate, we will see how work done affects the GPE of the crate. When you lift a crate of mass 5 kilograms from the ground to a height of 4 meters, how much work did you do on the crate? The work done, W, is given by W equals F times delta D, which equals 50 newtons times 4 meters, which equals 200 joules. The crate's GPE on the ground equals 0 joules. The work done on the crate becomes the GPE of the crate. So the GPE of the crate at a height of 4 meters equals 200 joules. In this case, the work done against gravity of 200 joules is equal to the increase in the gravitational potential energy of the crate by 200 joules. So W equals delta PE. In scenario number 2, which is about playing tennis, we will see how work done affects the kinetic energy. The kinetic energy of the tennis ball resting on the ground equals 0 joules. When a player hits the tennis ball with a racket, they apply a force and the tennis ball goes through a displacement. The work done here is W equals F times delta D. This work done by the racket increases the tennis ball's kinetic energy. So we can say the work done equals the change in kinetic energy of the tennis ball, or W equals delta KE. From these two examples, lifting the crate and tennis playing, we see that the work done on an object changes its energy, which is the work energy theorem, law of conservation of energy. Now, let us explore the thrilling sport of pole vaulting, where athletes use a combination of strength, skill, and physics to soar to new heights, literally. And behind every gravity-defying leap lies a fundamental principle of physics, the law of conservation of energy. The law of conservation of energy states that the total energy of an isolated system remains constant. In other words, energy cannot be created or destroyed. It can only be converted from one form to another. Let us assume that there are no friction losses in this scenario. The athlete eats a healthy meal, which is stored as chemical potential energy. As the vaulter sprints, the chemical potential energy is converted to kinetic energy. As the pole is planted and bends, most of the Ke gets converted to elastic potential energy in the pole. This elastic Pe is then converted to some Ke and a lot of gravitational potential energy as the vaulter is propelled upwards. At the very top, as the athlete has a momentary pause, all the energy is in the form of GPE. As the athlete is launched into the air, the GPE is transformed into kinetic energy. The GPE gradually decreases, Ke increases, and is at its highest point just before he hits the pad. Throughout the process, the total energy of the system stays the same. Happy learning! Thank you! If you enjoyed this video, don't forget to like and subscribe for more exciting explorations of science.